clarity and AMR verification, because this is a point of confusion that usually happens. People do not sometimes know the difference between the two, or they assume they are the same thing. And today we will finish it with explaining some things about carryover, because this is something that you'd have to do basically with every installation. Okay, at the end of each section, as I told you, I will stop and ask for your questions. Bismillah. So for the beginning, method validation and verification. Now, few important points. As I told you, or maybe you have read this presentation, I tried to base this presentation mostly on CLSI, because CLSI basically is, I would say, a body or a group of experts who basically gather every few years and put guidelines for the medical lab and sometimes for the hospital itself. So CLSI is very much recognized across the medical laboratory. And people generally, when they say it's CLSI, they just follow without asking many questions. So CLSI would be a good source, and generally it's very much detailed, and sometimes it's too detailed. That's why I chose to summarize what they have. And that's why this took such a long time. However, sometimes certain countries have local guidelines, and generally you must abide by the local guidelines, or if the lab is accredited by CAP, by JCI, by ISO, whatever it is, you have to follow these guidelines. So CLSI generally can be used if you do not have a local guideline, or if you do not have an accrediting body that forces you to follow certain protocols or guidelines or certain practices. Okay, and I'll explain to you at the end of this presentation, that is tomorrow, how do you exactly follow the order? Should I start using CLSI? Should I start using the local guidelines? Should I start using Stago guidelines? We'll discuss this tomorrow, okay? Now, for a start, what exactly is method validation? Is it the same as verification? Because often you would hear in the lab, I want to validate the machine after you do the installation. Now, method validation, if we want to be precise or accurate in our definition of method validation, if I created a test X, let's call it, okay? And it's a brand new test. No one ever heard of the test. And test X is designed to measure the amount of analyte Y. Okay, so when someone says, I want this test X, means that they measure Y. So how do I make sure that test X accurately measures Y? I have to test it in many different ways to actually confidently say that test X is actually appropriate for me to measure the analyte Y. Otherwise, maybe it's measuring the analyte Z. Maybe it has interferences. Maybe it's not precise. Maybe it has carryover. Maybe. So whenever a manufacturer creates a test, or creates a new reagent, or creates a new test, or modifies an existing test, I have, as a manufacturer, to validate this test. Means I have to test it very thoroughly. And this usually is testing that's done by the manufacturer, not by the lab, because it's a very hectic, very difficult kind of testing and very expensive. So the manufacturer will do this validation to tell you as a user that I have tested, I have validated this test very well, and it can be used to do this and to do that. Okay, so for example, Stago creates a new reagent for PT. Then Stago has to validate this reagent very well before they put it in the market, because they have to tell the user very confidently that we tested this reagent and it performs very well, which means you can use it as a user. Okay, so this process, validation, is not done by the user. It's done by the manufacturer of the test. One very important point, if the user changes the protocol, changes something in the reagent, changes the way the test is done from what the manufacturer said, this is no longer a manufacturer test. Okay, so if I change anything in the test, as the manufacturer says that I have to do it, this becomes something that is called a lab developed test. Means that the lab is completely responsible for validating the test again. Okay. However, if I, as a lab, follow what the manufacturer said, I don't have to do validation. I have to do something called verification. Verification is much less difficult than validation. You require less work. You have to do less things than validation. So verification is a minimized version of validation. Validation is a lot of work. Verification is much less work. Validation is done by the manufacturer. Verification is done by the lab. to verify what the manufacturer has validated. Okay, so verification, as I explained to you, it's done by the user, it's less complicated. And if the lab uses the protocol or the process or the test of the manufacturer as the manufacturer said, we do not have to validate, we just verify. Okay, so from this point onward, what we are talking about is verification. We do not talk about validation in this presentation because none of us is manufacturers. Okay, I just wanted to highlight this difference for you so you will understand when you read some documents the difference between validation and verification. For example, CLSI documents, a lot of the time they will have a section for validation, and that has to be followed by manufacturers, and they have a section for verification, which has to be followed by the lab. So if you do not know this difference between validation and verification, you might tell the customer you have to do X and Y and Z, but the customer does not have to do it. And you might actually fail the validation in the customer lab. So you have to be aware of this difference when you are reading documents or trying to work with certain resources. So moving forward. This is what I explained to you early on, but this is just a disclaimer of sorts. Now, trueness, precision, and accuracy. Before I speak about trueness, precision, and accuracy, there is a very simple concept, but that is often confusing. That is the concept of error, which is actually very simple, very intuitive. Error, when we are talking about a test that measures a quantity, for example, fibrinogen, clotting time, number of red blood cells, PCR testing, any kind of testing that reports a quantity that gives you a number. Okay, there is the actual quantity of the red blood cells, there is the actual quantity of fibrinogen in the sample, and there is the quantity that we are measuring. Okay, so there is the actual quantity, the real amount of fibrinogen in the sample, for example, and there is the amount that we are measuring. The whole point of us measuring something is to try as much as possible to know the actual quantity. The actual quantity is what is really in the sample. Okay, now since tests are never 100% perfect because reagents are not 100% perfect, humans are not 100% perfect when they are preparing reagents, analyzers are not 100% perfect, there is always a small difference, sometimes a big difference, you never know. There is always a difference between the actual amount that is in the sample and the amount that we are actually measuring and reporting to the patient. This difference between the measured quantity or amount and the actual quantity is called error. Okay, so any difference between these two is called error. There are many different types of error, but I don't want to complicate things. So, you know, there are pre-analytical errors, the errors that come before you test the sample, errors in collection, errors in storage, errors in transportation. We will not talk about these. There are post-analytical errors, errors that happen after you analyze the result. Errors in reporting to the clinician, errors in transmitting to the LIS, errors in sending the result to the clinician, wrong unit, wrong number, etc. I don't care about this. What we will talk about, what we are trying to work with here is called analytical errors. The errors that you will see or encounter when you are actually measuring something, when you are actually analyzing the sample. Okay, these are called analytical errors, errors that you will see when you're analyzing the sample. And this is what matters to us when we are doing verification. When you are doing the verification process, when you are installing a new machine, for example, you do not take care of, we do not care about pre-analytical. We do not care about post-analytical. We care about analytical. That's why I want to basically explain what this is, okay? Now, total analytical error describes the whole difference between your actual concentration of whatever in the sample and whatever you are measuring. So why did I say total? Does that mean there are subcategories or other types of error? Total error means all types of error, okay? So what are the types of error? There are two primary ones. There is random error, which means it's not something that is consistent. And there is systematic error, which is something that is consistent, okay? What does this mean? Now, systematic error is something, as I told you, it's consistent, it's predictable, it always works in the same way. For example, my measurement is always higher than the actual measurement by 0.2 units, always. Or it's always less than the actual measurement by 0.5 units, always. So because it always happens in the same way, it's predictable. We call it systematic. Okay. Random error, however, is not predictable. You never know how it will proceed. One time the difference is 0.2. The other time the difference is -10. The third time the difference is +5. You never know. That's why it's called random. It's unpredictable. So these are the main types of error that we work with: systematic and random. The combined error, the combined systematic error and random error, is called total analytical error. Okay, so these are the two types of error. And these are important because when we talk about precision, we're talking about random error. When we talk about bias, we talk about systematic error. What is the importance of that? When you are doing verification, you absolutely must know how to estimate bias. What are the guidelines from the manufacturer? How to estimate the precision? What are the guidelines from the manufacturer? Without knowing this information, you cannot really understand what you are doing very well. Now, there are some terms that you will see in documentation. What are these terms? Trueness basically is how much is the bias from the actual value when I'm doing a measurement. How different is my measurement from the actual value? Just a small reminder, the actual value means what is actually in the sample. The difference between what is actually in the sample and what I am measuring is called bias. Okay, so trueness essentially represents bias. Okay, when I'm talking about trueness, I want to know how much bias is in our measurement. Technically, the definition of a trueness is the actual difference between my measurement and the actual value if I measure 1,000,000 times, for example, or infinite times. So it's the average difference between my measurement and the actual concentration. Okay, because if I just run a single test and I see a difference between the actual measurement and the actual concentration and the measured concentration, it could be random error. I don't know. It could be bias. It could be both of them. That's why for me to estimate bias or trueness, that is, they are basically one or the same. I have to measure a very large number of results. You can never estimate bias from a single run usually. Okay, bias requires you to run many, many different points. How about the precision? Precision is the inconsistency between multiple measurements. So if I measure my sample 20 times, 30 times, 1,000,000 times, precision tells you how consistent are your measurements. I don't care if they are different from the actual value. I just care how consistent they are, okay? So trueness, I care about how close I am to the actual value. Precision, I don't care about how close I am to the actual value. I care how close are my measurements to each other. How consistent are my measurements to each other, okay? So trueness pretty much represents bias. Precision pretty much represents random error, or we call it imprecision, okay? Now, accuracy is not something that we can really quantify, because we can quantify bias. We can quantify imprecision. Bias, I can quantify it by the difference from a certain value. Precision, I quantify it with CV%, with the standard deviation. Accuracy has no measurement. There is no percent accuracy, so to speak. Okay, accuracy basically tells me overall how precise and how true is my measurement. So accuracy combines precision and trueness. That is the difference between accuracy and the trueness, because some people think trueness, accuracy are the same. CLSI tells you no. Accuracy combines trueness and the precision. If you look to this drawing to the side, let me put this pointer. No pointer. Okay, there's a pointer. Okay. So if you see, as you go up diagonally, high trueness and high precision, accuracy is increasing. So accuracy increases with the increase of both trueness and the precision, because accuracy is a combination of trueness and precision. Understood? So this is very important to understand, because a lot of people confuse these two. And later on, as we speak more about verification, this can create a confusion. Okay, so this is more of further details what we are talking about. Okay, I will not detail more about things that are already written here. We spoke about this as well. Okay, so as I told you, total analytical error is composed of both systematic error and random error. Systematic because it's consistent, it's predictable. Random error, it's because it's unpredictable, it's random, it's inconsistent. Okay, if you combine these two, we say, or we are describing the total analytical error of the test, because the test can be inconsistent, the test can be biased. Okay, both of these things combined, we call them total analytical error. Can the test have random error and at the same time have systematic error? Absolutely can be. Can a test have only systematic error or only random error? Absolutely can be. We have ways of estimating both of them separately, but that's a different story for another day. This is also what I explained to you. This is just more text for you to read later on. Now, there is a term that is often confused with total analytical error. As I told you, total analytical error describes the total error that we have observed in our measurement. Okay? Yes, Sally, I see you raise your hand. Tell me, please.
Yeah, I just want to ask one thing on this point, like the
Hmm.
trueness and the accuracy. Like both of them,
Mhm.
we need to target or hit the mean. يعني what's exactly the main difference between both of them?
Okay,
يعني
see,
نص كتير.
accuracy, as I told you, accuracy is not something that you can quantify. So accuracy itself can never be a target. We cannot say that we want our uh, test to be 10% accurate. There is no such a thing. Accuracy is an abstract. Okay, so you say your test is accurate or is not accurate, but how accurate it is, it's not something that is technically correct. We can say how much trueness we have and how much precision we have and how much total analytical error we have. Okay, so you can consider that accuracy is the closest thing to total analytical error. Okay, because total analytical error describes both trueness, which is bias, and imprecision, okay, which is how inconsistent your results are. But accuracy itself, you will not see it. You will not see accuracy described in percentages or in units or in grams per liters, for example, because accuracy is an abstract. Okay,
Okay,
understood,
thank
Sally?
you. Yes, yes, thank you.
You're welcome. So now, what is the difference between total allowable error and total analytical error? Total analytical error is what you actually measure from your analyzer, from your method. That, for example, I can say the total analytical error is 3% for this analyzer. Maybe the analyzer next to it is 4%. What I'm trying to say is this analyzer has this much error based on the testing I have done as a user. This analyzer has this much error based on the testing I have done as a user. Total allowable error is the maximum amount of total analytical error that your analyzer is acceptable with. So for example, Stago comes to you and says to you, the total allowable error for PT second should be 5%. So you go test your analyzer, you check trueness, you check precision, and you find that the total analytical error equals 3%. Okay, so 3% is what I have actually obtained when I tested the analyzer. But Stago says you are allowed to have a maximum of 5%. But I got 3%, so means I am less than the maximum limit. I am okay. Okay, so total allowable error is the maximum you are allowed to get before you fail something. So for example, CAP says, if you want to work with us, if you want to be CAP accredited, then your analyzer cannot have more than this much total allowable error, 10%. You test your analyzer gives you 13% total analytical error. So you actually, from your results, you got 13%. You are higher than what you are allowed to get, which is the total allowable error. So you fail, okay? So the total allowable error is the maximum amount you are allowed to have of the total analytical error. Of course, there are more details, but this is to simplify the idea. Understood? So total analytical error does not equal total allowable error. Allowable is the maximum you are allowed. Total analytical is what you have actually obtained from your testing. Okay? Now, as I explained to you, trueness is pretty much synonymous with bias. If I want to say how true is my method or what is my trueness, I have to quantify bias. So trueness is the concept. Bias is what we actually measure, what we actually quantify. I can say that I have 3% bias. I can have, for example, 2 IU per ml bias. So bias is what you quantify, and bias and systematic error are the same thing. Two different names for the same thing, pretty much. Okay. And what is it? Okay, we'll come to random error later on. And to quantify bias, I have to know the actual concentration in the sample, or I have to have something that has a known concentration, something that is very accurate. Because how can I say that there is this much difference between what I measured and between the actual value, and I don't know the actual value? Okay, for example, I run a fibrinogen test and it says 3 grams per liter. I say, oh, okay, I have 1 gram per liter bias. How do I know I have 1 gram per liter bias? I don't even know the actual concentration, right? What if the actual concentration is 10 grams? Then between 3 and 10 grams, that's 7 grams per liter. Okay, so for bias, you absolutely must have a known concentration to compare to. This is absolutely crucial for bias, because remember, the definition of systematic error or bias or trueness pretty much is the same. The difference between the measured value on average and the actual value. Okay, if you don't have an actual value at a very accurate value, you cannot estimate bias. It's not possible. Okay, that's not the concern for precision. As I told you, for precision, for random error, I don't care. For random error, all I care about is how consistent my results are from run to run. This is the main difference between the two. Okay, so the current guidelines tell you how do you estimate bias. For example, I can do a comparison with an analyzer that is validated. I can use external QC materials. I can use calibrators, etc. All of this is fine. Okay. I think we have said this pretty much. For Stago, for example, we offer systematic error limits. Okay, they are called correlation limits. We will come to that later on. Now, practically for the lab, because I don't want to just give you guidelines, and then it's not something that can be practically applied. For most of the labs that you work with in the field, the most practical way to estimate bias is by running a comparison between the analyzer you want to test and an analyzer that is already validated or verified, so to speak, okay, to be more accurate. For example, CAP tells you if you want your analyzer to be CAP accredited, you have to compare your analyzer to another analyzer that is already CAP accredited, and you have already passed the external quality control on that analyzer you want to compare to. Okay, because they consider the other analyzer as accurate 100%, theoretically at least. Okay, so practically, how do I estimate bias or systematic error for us working in the field? You should do comparison. Okay, the other methods are not so easily obtainable and they are generally expensive. So for example, what do I do? CLSI tells you comparison should be done on at least 40 patient samples. 20 samples may not be very statistically reliable. Okay, so CLSI tells you if you want to do a very good comparison, I know this may be more expensive for the customer, but I have to tell you what the guidelines say. What the customer wants is a different story. We have the guidelines, customer wants to follow, it's up to them. So CLSI tells you a comparison should be at least 40 patient samples, different patient samples, not the same sample 40 times. 40 different patient samples, okay? Run on one analyzer, then run on another analyzer that is already verified, that we know is very good, very well maintained, etc. Now, very crucial for you to know, never compare samples that were treated differently. Means never compare a sample that was fresh, then was frozen, then you run it after you thought on the other analyzer. You will definitely create differences. because different treatments, different collections, transportation, freezing, all these samples will create differences that are not actually bias. These are differences because you process the sample differently. Okay? So if you do this, later on you look like you have a bias that is not actually bias. So always remember, when you do a comparison, never compare samples that were treated differently. Okay? And when you want, for example, to compare reagent to reagent, analyzer to analyzer of the same type. These things I think you should already know by now, so we'll not discuss them very much. Now, the data that I get after I do the comparison, how do I do it? There are many different ways. Okay? The statistics and how do I do it? How do I process this? How do I process that? I will not go over that because it's very, very, very extensive. I give you a few examples later on in the comparison section, and you will see it should be simple and straightforward following Stago guidelines, because otherwise things will get very complicated, and I don't want to complicate things more than they already are. My point is to simplify. Now, from Stago, what are the documents that I can use for bias calculation? The claim from Stago is a document called SAV4012. It's called correlation claims. Okay? Correlation claims tells you if you compare compact max to compact max, PTT automate to PTT automate, this is the acceptable difference. You cannot use this document to compare PTT automate to CKPrest or PTT automate to Siemens reagent or PTT automate to Werfen reagent. You compare same analyzer to same analyzer, same reagent to same reagent. Where did the Stago get these percentages? How did the Stago decide on these percentages? This is done by Stago based on French guidelines. No need to discuss the details, okay? So what do I calculate from this comparison? Something that we call the mean bias percent. How much is the average bias that you have when you do this comparison study? So how do I calculate this? I have run, for example, my 40 samples. I will calculate something called mean of row differences and mean of averages multiplied by 100. Sounds very complicated. It's not. You will see. Very simple. So in this example, I have 1, 2, 3, 8 samples, for example. Okay. Sample X, sample Y. So let's say X is my good analyzer, the one that's verified. You did everything, perfect analyzer. Y is the new analyzer that I want to test. Okay. So I check the differences. X minus Y, X minus Y, X minus Y. Can I do Y minus X? You can do Y minus X. Okay. It's just that the average value will be the opposite signal. It will be plus. Okay. So if I do Y minus X, it will be just the opposite. Just for you to know, for your information, most of the current guidelines and common practices, we do X minus Y. X is the good analyzer, the perfect analyzer that's already verified. Y is your testing analyzer. Okay, so if you go read some documents and guidelines, you'll not be confused. Why is this always X? Why is this always Y? It's just a convention. Okay, this is how things normally work. So row difference is the difference between X and Y. 13.2 minus 13.5 is minus 0.3. Then I calculate the average X, average Y. So all of these, the average of all of these is 19.925. The average of all of these is 20.27. This minus this equals this much. Okay, so we keep this number on the side. And we call this number the mean of row differences. See, row difference, the mean of the row differences. Understood? Okay, so we have now this number. Where do I get the other number, the mean of averages? This one plus this one divided by 2. Basically, I calculate the average of the averages of X and Y. Okay, so mean of averages is the average of these two numbers. The mean of row differences is the average of the difference between these two or these two, pretty much the same. Then what do I do? Mean of row differences divided by mean of averages. So mean of row differences divided by mean of averages. It will give you a value of minus 1.74. So the mean bias for this test, for example, is minus 1.74. Is it acceptable? Is it not acceptable? I will open Stago document. Let's say this is PT, for example. So I do comparison for PT. I calculate the mean bias. It says minus 1.74. I open Stago document. Stago document says mean bias acceptable for this test is 3%. I passed. Okay, simple as that. Stago says no. The mean bias acceptable for PT is 1%. Means you fail because you are higher than 1%. You say, yeah, but this is negative signal. The sign doesn't matter, okay, in this case. The sign just tells you it's negative bias or positive bias. Negative bias means your test analyzer is reading lower than your good analyzer. If it's positive sign means your test analyzer is higher than your good analyzer. So the signal just means the direction of bias. That's it. Okay, so for example, let's look at this. For PT, this is from the document SAV4012 I told you about. For PT, Stago says the R value should be this much. I'll explain. The slope should be this much. I will explain. The mean bias from average is a plus minus 8%. How much is our value? Minus 1.74. Is it less than plus minus 8%? It's less, so we pass. How about the intercept? I will explain in a second. Okay, so any questions until this moment? Because I know things may be a bit heavy by this point. Any questions before I proceed? Yes, Sally.
Yes, Laith. I have two questions. Now, the first
Sure.
question, should we use a normal plasma? Or we could also use the abnormal, like it's a random normal and abnormal plasma samples for the trueness. Second,
Mm,
if I need to compare with another machine or another machine in the lab, can I
mm.
use the same concept? No, or it's gonna be a different one.
Now, when you want to do comparison, ideally comparison is done with patient samples. Do not use the QCs. Okay. The reason is many reasons really. Okay, but just to keep things simple, you should use patient samples that should span as much of the measuring range as possible. Okay, usually QCs are just 2 data points across the measuring range. Plus, QCs are lyophilized and sometimes they're liquid, they're not even a plasma. So QCs do not necessarily represent the way the machine would deal or would interact, or your reagents would interact with actual patient samples, actual patient plasma. So you should always use for comparison patient plasma. If you absolutely have no way to use patient plasma, then QC is the exception because we have no choice. Okay. The second point, these values that you see from Stago document are applicable only for Stago analyzer to Stago analyzer of the same type. So satellite max to satellite max, compact max to compact max, R max to R max, and only for the same reagent. You cannot compare neoplastine to neoptimal. You cannot compare, for example, uh, deficient factor 8 to immunodef factor 8. You cannot compare CK-Press to PTT automate, okay? It must be the same reagent, the same analyzer. Understood? So you cannot compare to another analyzer from another manufacturer. Actually, for the vast majority of tests, we do not have any way to accurately or to properly compare to another manufacturer's results. Few exceptions are maybe INR, for example, okay? But for most parameters, we do not have guidelines, Stago or other manufacturers. There are no guidelines that tell you the acceptable difference from another manufacturer is this much or that much, okay? Which is one of the challenges in the field of coagulation in general.
So we can use the normal samples here, like a normal patient samples.
Yeah, you have to use normal patient samples as low as possible, as high as possible, and everything in between. I know practically that's not always feasible, but try as much as you can.
Okay, thank you.
You're welcome. Any other questions other than Sally's? Remember, guys, the whole point of this session is to answer your question more than anything, because I know this is quite technical. Okay, so I assume none. Yeah, so Sally, for example, this answers part of your question. So one of the exceptions for comparisons between two different systems, if you want, for example, to compare Stago to Sysmex for INR results, because this is a very common comparison that happens in the lab. ICSH, which is one of the bodies that offer guidelines in the field, they say it is acceptable that when you compare at least 20 samples, 20 INR results between Stago and Werfen, Stago and Sysmex, whatever, that at least 85% of the results or above must agree to a 0.5 INR difference. What does this mean? So for example, I ran 100 samples, okay? 100 on Stago, and the same 100 I run them on Sysmex. More than 85% or 85 of these samples must have a difference of INR less than 0.5 to say that this comparison is acceptable. Okay, and the INR should be in this range. Understood? This is an exception. Most of the other parameters do not have such guidelines for you to compare between them. Understood? But because INR is something that's very important, there was some research done on the topic because it's a very common thing that happens in the lab. Okay. Now, the slope, intercept, and the R value. R value is something called correlation coefficient. Sorry, it's not regression. I have to fix this. It's called correlation coefficient, okay, which is in this table. Remember, this is a Stago's document. So, correlation coefficient, slope, and intercept, okay? These values, when you are doing a comparison, they should pass Stago criteria from the table I have just shown you. Then how do I calculate these values? We don't have a tool that does that for you. Okay, we can make an Excel sheet, but we don't have an official document that I can share with you and I tell you this is a Stago's official document. These are things that are very easy to calculate. You can even go on Google and type, how do I calculate slope, intercept, R value? There are even web pages that calculate this for you. It's very simple, okay? Point is, when you calculate the slope, the intercept, and the R value, they should fall for your compared samples in the range of these values for us to consider the comparison passed. Plus, of course, this one that I explained to you already. So all these four things must be within Stago criteria for us to say that the comparison has passed. How do I calculate this, and the intercept? Go on the internet. What does regression correlation mean? What does slope mean? What does intercept mean? This is not a maths class, so I will save you the headache, okay? It doesn't matter really what they mean. I don't want to overcomplicate things. Okay, now, one common misconception that people fall in all the time is that when they do comparison, they use a Stago claim. For example, for PTU, so it was average mean bias, or average bias percent, sorry, is plus minus 8%. So they say, oh, okay, 8%. So the result on X analyzer minus the result on Y analyzer, how much is the percent difference? Oh, okay, it's 5%, passed. This is not how it works. You cannot use Stago claim to compare between individual samples. You have to run the full comparison, then calculate things the way I told you. Then after the calculation, the number at the end, the minus 1.74 in our case, it is the one you compare to Stago claim, not the difference between individual samples. Okay, this is very important. Now, one thing that you will see when you are looking maybe at documents other than CLSI, the terms sometimes in the field of quality assurance and quality control and all of these are not always used the same way between different guidelines. So CLSI tells you very clearly, accuracy is trueness plus imprecision, okay? Accuracy is not the same as trueness. Some publications, some guidelines, they tell you accuracy and trueness are the same, okay? And they are verified in the same way. And accuracy can be verified sufficiently with comparison. I am not a scientist in the field, so I cannot say one of them is wrong, one is not, because obviously they're experts in the field, but you may have these disagreements. But I told you, for me, I'm following CLSI because it's a very solid standard based on the opinions of experts, okay? So we will not go through this point. But I just wanted to clarify it because it can be very, very confusing to know why is it that accuracy is sometimes used the same way as a trueness. We will not go through this, okay? Just know that you will see this, and it's not something that's standardized, unfortunately. I think I'll skip this. Okay, by the way, TAE means total allowable error. Sorry, total analytical error, okay? Total analytical error is the thing that you actually measure yourself as a user. Sometimes you'll see TEA. TEA is by convention total allowable error, okay? I know it sounds very, very weird. Why is this TAE and that one is TEA, but it's by convention how most labs use it. Uncertainty of measurement is something that we'll come to later on, okay? So I will not detail much here. Now, when would my trueness or bias be too much? How do I fix it if my bias is too much? It's unacceptable based on the Stago criteria. Bias, as I told you, is mostly a predictable amount of error. So calibration is one of the common reasons, calibration failures. Another common reason is issues with reagents. For example, a reagent was prepared with the incorrect amount of distilled water, for example. So there can be reasons, but generally they are obvious. Okay, your calibration will be clearly not very good one if, for example, you compare to the previous calibration. Okay, so you'll see there are some clear things. So most common thing I would say if you have problem with bias is check your calibration and check your agent preparation and storage. These are the most common reasons. Can there be other reasons like hardware failures? Yes, but these are much less common. Okay, so I will not spend much time on this point. Now, when you work with a precision and you want to estimate imprecision, imprecision is the opposite of precision. How precise you are can be also described by how imprecise you are. Okay, imprecise means that you have bad precision. But anyways, not to waste our time on words, it doesn't matter much. Okay, if you say precision or imprecision, we're trying to quantify how consistent your results are. Okay, I don't care about the words. Now, how do I quantify imprecision in my sample? Okay, or random error? They are the same thing. How do I quantify, sorry, imprecision in my system, analyzer, reagent, all of these things combined? You can either use quality control materials, you can use patient samples, you can use whatever plasmas you want. Ideally, we want to use something as close to the patient samples that we are running day to day as possible. Why? Because maybe quality controls, because they are lyophilized, they're stabilized, they show you less imprecision than an actual patient plasma. So ideally, when you want to do comparison, when you want to do the imprecision studies, when you want to do any studies, you should use as much as possible patient samples because they represent the way your analyzer interacts with your daily sample, the way your reagents interact with your daily samples. To be honest, sometimes you might use quality control materials to do comparison studies or precision studies, and you'll find that, oh, it passes, it's a great. But the moment you try to do the same experiment with patient samples, you will see that you may have a failure. Okay, I have seen these cases plenty before. So try as much as possible, use patient samples. However, sometimes some precision studies, for example, require you to do this work over 4 or 5 days. There are no patient samples that are stable for 4 or 5 days for coagulation. So unfortunately, this cannot be always the case that you can use patient samples. Okay. Now, for precision, you will hear these terms a lot. Simple precision, intermediate precision, complex precision. What does that all mean? Isn't it one precision? Why now we have 3? I'll keep it simple. Most commonly, we work with simple precision and complex precision. Okay? We have stock guidelines for that. We have documents for that. Things are very easy. What is intermediate precision? Usually, it's not very relevant for our work in the field. Okay? I'll explain. Now, why do we have 3 other types? It's the same. With in-run precision, repeatability, simple precision, intra-run precision, it's all the same. Different names for the same thing. Why do we have so many names? I wish I have an answer for you, but that's what we've got. Okay, so all of these, they are exactly the same thing. It's basically when you take a sample or a QC and you run it 10, 20, 30, 40 times all at once. Okay, you don't split it morning, evening. You don't split over 2, 3 days. No, you do all these 10, 20, 30 runs right now. We call this simple precision, using the same reagent, the same operator, the same analyzer, the same pipetter, for example, the same everything. The only variation is the measurement results from one run to the next. Intermediate precision is when you introduce some variation. Okay, but generally most guidelines, most accreditation bodies, most local guidelines do not care about intermediate precision. Okay, so I will spare you the effort. I just put it here for a clarification that if you see it, most often it's irrelevant. We don't care about it. Okay, what is then complex precision or within lab precision or reproducibility? All are the same thing. This is when you run your precision over extended period of time. Why? To introduce more variability. Because in the lab, normally you don't have the same technician working 24/7. You have multiple technicians. Sometimes you may have variability in temperature from morning to evening. Humidity changes at the lab. Sometimes the electricity changes. Sometimes the performance of the analyzer changes over time. The stability of the reagent changes. Different vials come in, different loads come in. So the point of complex precision is to test all this variability and its effect on the results that you are running. Okay, so complex precision is done by running the test at more than one day, preferably morning and evening. You can add afternoon, depends on the guidelines you are following. Okay, and then we will see the results at the end. And it's the opposite of simple precision, because simple precision, nothing varies. The only difference is the difference between your results. Okay, complex precision, no, we have different technicians, we have different reagent vials, we have different conditions in the lab, etc., etc. Okay, now, one point, as I told you, sometimes you will go from one source to another and you will see words used differently. For some labs, for some guidelines, for example, complex precision is called between lab, not within lab. Okay, I don't care about this. I told you I'm using CLSI here, but the point is the same. What we care about usually is complex precision and simple precision. In Stago's words, they are called repeatability and reproducibility. So in Stago documents, you see repeatability claims and you see reproducibility claims. This is what I care about. So how do I do the testing for precision? Generally, it's very easy. For repeatability, at least you will do 10 runs of the same sample of the same reagent. Of course, you cannot do 5 runs. You can press 5 runs PT to automate. It has to be the same reagent. Okay, we cannot play around with these things. It has to be the same reagent, same analyzer, same technician, same everything. Reproducibility is according to CLSI guidelines. Stago follows pretty much the same. You do 5 runs a day in one batch. You can do 5 runs in the morning, for example, or 5 runs in the evening. It's up to you. 5 consecutive days. Okay. And this is 25 tests for each level of a QC. Or if you have 3 levels of a QC, use 3 levels of a QC. The more, the merrier. Okay. But you have to balance. If it's too much cost for the user, maybe you have to keep it at 2 levels. That's a different story. So at the end, we get 25 runs for each level of AQC. And then we just compare to Stago claims. I'll give you examples. Now, after I do the 10 runs, the 25 runs, the 30 runs, 1,000 runs, what am I trying to compare or do? If you remember in comparison, we had some simple calculations and we compared these calculations to Stago's limits. Same concept here. I will take my 10, 20, 30 runs, then I will calculate something called coefficient of variation, CV%, or standard deviation. Okay? CV% and standard deviation, they express the same thing. They express imprecision. They just express them in different ways. CV percentage is expressed as a percent. Standard deviation is expressed in the same unit as the main test that you done. Okay? So for example, if I'm working with fibrinogen a gram per liter, I express the imprecision of fibrinogen gram per liter in CV percentage. Standard deviation, I express it in grams per liter. Okay. Now, standard deviation, this is an important point that a lot of people may miss. Standard deviation is usually used for parameters with very low readings, 0.1, 0.2, 0.3, like D-dimer, antitony, and all these, because CV% is artificially very high. CV% is more suitable for parameters with very high readings, like factor 8, like factor 9, von Willebrand RCO, and so on and so forth. Okay, the document that we use is called SAV 4013, repeatability and reproducibility limits. I will give you all these documents. You have seen them in WhatsApp group. Now, precision limits, as I told you, are not specific to the patient, to the sample type. Okay, they apply to QC samples if you use them, calibrators if you want to use them, patient samples if you want to use them, pooled plasma if you want to use them, all the same. Okay, so you will not see repeatability limits for QC or repeatability limits for calibrator. This does not exist. It applies the same to all of them. Okay. Now, finally, one last thing. If you have a test, and that applies to all kinds of testing, Stago, coagulation, hematology, chemistry, all the same. If you do not have a manufacturer claim, then you can go to some guideline, local guideline, international guideline, and you look for the total allowable error. The acceptable amount of precision is 50% of the total allowable error for that particular test. For example, if you go to CLIA, which is something used in the US, CLIA for PT, total allowable error for PT is 15%. Stago did not offer me precision guidelines. So what do? 50% of the 15% becomes your precision limits. So 50% of the 15%, how much? It's 7.5%. The same applies to bias, but for bias, I don't use 50% of the total allowable error. I use 25%. Okay? This is something that you will not normally find from Stago. You will not find this information from Stago, but it's something that would be useful for you to use at some point. Anyways, so some people, they see that, okay, CV%, no, my user insists to use standard deviation. I cannot now pass the validation. It's simple because this is something that comes very commonly. You can convert a CV% into standard deviation or standard deviation into CV% super easily. CV% equals standard deviation divided by the average by 100. Now, this average, this is very important. This average is the average of the 20, 30, 40 runs that you ran on the analyzer to verify its performance. Okay, so the average shows to do this conversion only after you run your experiment. Understood? So for example, I ran PT 20 times and the average was 14 seconds. The acceptable CV% from Stago is 1.5%. So how do I know the acceptable SD? The customer insists they want to have the acceptable SD. So I say, okay, very simple. CV% equals standard deviation divided by the average by 100. I don't know the standard deviation. I want to calculate. So 1.5%, the acceptable value from Stago, divided by 14, the mean of the runs that I made on the analyzer, by SD. You do some math around. Okay, I'm not here to teach you math. The standard deviation acceptable for this 20 samples or 20 tests run is 0.21. If you calculate the standard deviation of your 14 runs, okay, then it will be this much, and it will be less than 0.21, it's acceptable. More than 0.21, it's not acceptable. Simple as that. You will skip this stuff because it's just there for you to read. I explained to you this point, so I will skip. It's just text. Okay. Any questions before we move on from precision? No questions? Well, if you understood all of this, then this is impressive. I would say good job. Yes. Okay. Now, one last very important point. When you install a new analyzer, usually the very first verification test is done by the service engineers, which is repeatability. I take a patient sample or a QC and I run it 10 to 20 times, and I check it against the Stago claims of repeatability. If it fails, means something is not functioning properly. And usually that's something that has to be addressed by the engineer. Okay, so always, always, always do not do any analyzer or system verification work before precision passes. Because if your precision is bad, everything else will fail. Your linearity will fail. Your carryover will fail. Your comparison will fail. Everything will fail. So always the first step in your verification work, check that the precision passes. If it passes, proceed. Precision fails, stop all the work because all of it will fail. Call your engineer, ask him to verify what's going on if you cannot detect the issue, okay? It can be a bad valve, it can be a bad needle, it can be a million things. Understood? So this is a very, very important point because again, precision is bad, everything else is likely to fail, calibration included. Okay, I think we don't have much to add at this point. we will move to linearity and AMR verification. Any questions about the previous two sections before I move to linearity? So all is good, no questions? All right. I will ask you a question. Did any of you use the biological test sheet before? I believe some of you have done it.
Yes, yes, like we do it.
Okay, so it's routine work for you. That's good. Yes, because people who have more experience with the analyzers must have definitely seen this biological test sheet. The biological test sheet is very simply an Excel sheet where you fill in your 10 runs of QC or patient sample, and it calculates the CV and SD for you and tells you that it passed or failed. Okay, so that's what the biological test sheet. It's a very strange name, but it's one of the tools that I have shared with you on the WhatsApp group. Now, linearity. Linearity might sound like a scary concept for someone who's not very familiar with it, but linearity is very simple. Now, imagine the following. I have a patient sample with 5 grams per liter of fibrinogen. If I dilute this sample 1 to 2, then it should give me 2.5 grams per liter. It's half the amount of fibrinogen. If I dilute this patient sample 1 to 4, it should give me 1.25 grams per liter. If I dilute this patient sample 1 to 8, then it should give me 0.625 grams per liter, right? So it makes sense. If I dilute half, I should get half the amount. If I dilute quarter, I should get quarter the amount of fibrinogen in the initial sample. Okay, so this is something that I expect from the analyzer to be able to do. The more I dilute, the more the results will decrease proportionally to the dilution. Now, this is something that I must verify that my analyzer can do, because a lot of tests, they are diluted, and they can be diluted further sometimes based on some conditions. For example, the dimer is not diluted normally. But if the result is higher than 4 micrograms, the analyzer will dilute 1 to 5, then it will rerun the test. Now, if the analyzer dilutes 1 to 5, but the result does not decrease by 5 times, for example, the dimer is 10 micrograms, and the analyzer does a dilution 1 to 5. Now, when you dilute 1 to 5 out of 10 micrograms, you should expect 2 micrograms reading. Analyzer gives you a reading of 7. How come I am diluting 10 micrograms 5 times and I get 7? Doesn't make sense. Okay, so this is wrong. This is unacceptable. So linearity simply verifies that with dilution of these samples, for example, when I dilute a sample multiple times, the reading that I am getting is proportional to the dilution that I am making. Okay, if it's not, means that I have something wrong with my system. My system cannot measure things accurately. So linearity must be verified before the customer starts to use it. Because if at some point we do some dilution and things do not work very well, you will get wrong results for the patient. So if I have one sample, for example, linearity sample, let's call it, and we do multiple dilutions. So dilution 1, dilution 2, dilution 3, dilution 4, dilution 5, as you see. As the dilution increases, okay, or you can go through it the opposite way. As the dilution increases, the value decreases, doesn't matter, okay? Always the true value, the actual value in the sample, increases in the same manner as the measured value, or the measured value, sorry, increases the same way the true value increases. So let's say this is your 10 grams per liter fibrinogen. If I dilute the sample more, then of course things will drop. If I dilute the 10 grams 1 to 2, I should get 5 grams per liter. If the machine gives 5 grams per liter, very good. If I dilute a sample that has 10 grams per liter 1 to 4, if the machine gives you 2.5 grams per liter, very good. This is what I'm expecting. But if I dilute the sample 1 to 4 from the 10 grams per liter and the machine says, no, this is 6 grams per liter, this is wrong. Okay, the machine is not measuring things correctly. So if the measurement of the analyzer is proportional to the dilution that is made to the sample, we say the measurement is linear. Why linear? Because if I put it like this on a curve, it looks like a straight line. Very simple. Understood? Now, the Colored lines, I put them to test you, that you understood this concept well. This one is linear. This one is linear. It's written here. The blue one is not linear. Why did I say the blue one is not linear? It's straight here, right? Why did I say the blue one is not linear? Does anyone have an answer for me?
Because
No.
of the ending of the line, it's not linear, like not straight.
Exactly. So my test, the blue line, or the test that the blue line represents, it's linear, 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 linear. Up to this point, it starts to curve. Means I am doing more dilutions, but the machine is reporting incorrect results. Okay, so for example, again, 10 grams per liter. If I dilute 1 to 10, I should get 20 grams per liter. Machine says, no, this is 3 grams per liter. This is incorrect. Okay, so if you have a non-linearity in your curve, anything after the point where you see non-linearity, measurements are unacceptable beyond this point. So for example, if you look at the blue line, things are linear up to this concentration. Okay, beyond this concentration, do you see it starts to curve? Then I say my method is linear up to this point. It's giving proportional results to the dilution up to this point. Beyond this point, it's non-linear. This means I cannot report results beyond this point. Why? Because the results that I get are not proportional to the dilution. They are simply wrong. Okay? This is linear. This is linear. Why? Because it's linear all the time. All the time, the measured value is proportional to the true value. Is this concept correct? Any questions about this point before I proceed? Because if you do not understand this concept, the rest is meaningless. Any questions before I proceed? All right. Now, one very important point. When I say a test is linear, okay, I do not mean the test is accurate. I just mean that the measured value changes proportionately to the change in true value. Your method can be linear, but can be completely wrong. But you just said that, oh, 10 grams per liter should give you 1 gram per liter. It should be accurate. Yes, this is to simplify. Linearity does not mean that your method is correct. It just means that the machine's reading are proportional between the measured value and the true value. Proportional means maybe the true value increases by 1 gram and the measured value is increasing by 2 gram. If the true value always increases by 1 gram and the measured value proportionately always increases by 2 gram, they are perfectly linear, but they are not correct. Okay? That's why I told you linearity and AMR verification are different. Linearity does not care about if your value is accurate or not. Linearity just cares that the higher the dilution, okay, or for example, the higher the true value, the higher the measured value. The lower the true value, the lower the measured value. They are proportionate. That's it. It does not care about accuracy. Understood? That's why linearity is not the same as AMR verification or calibration verification, because a lot of people mix these two. So linearity is simply this. True value increases by a certain amount, measured value increases by a certain amount, and they're always the same. So I say they're proportional. True value increases 10, measured value increases 20, then measured value increases 30 on a different day. This is not linear. Okay, because it keeps changing. They should always be proportional, then I say they are linear. Okay, and this is pretty much what's explained in this slide. Any questions about linearity before I proceed? So I assume all is good. All right. Now, the concept of AMR. AMR is analytical measuring range. What does this analytical measuring range mean? It's very simple. If you open the kit and search for any test from Stago, most tests, not all of them, Stago says that this test can measure between this much and that much. For example, Stago says that the analytical measuring range for factor 8, for example, is 0.7% or 3%, sorry, to 150%. Means Stago tells you that my analyzer and reagent system can measure things accurately between 3% and 150%. So the analytical measuring range is what the manufacturer is claiming that their system can measure accurately. Okay. Again, analytical measuring range is the range that the manufacturer claims on paper that their analyzer can measure accurately. Now, since the manufacturer claims it, I have to verify it. Okay. If you remember from the beginning, verification means I have to verify what the manufacturer is claiming. That's what verification means. So the manufacturer is claiming that their analytical measuring range is 3% to 150% for factor rate. Okay, so this is what the manufacturer claims. Then I have to verify it myself to make sure it's true. Now, the condition of calling something an analytical measuring range is the sample cannot be diluted or concentrated outside of the normal protocol. What does that mean? But factors are diluted 1 to 10. Yes. Focus on the usual assay process. So Stago says when you run the assay, the factor sample or the factor test, sorry, you have to always do 1 to 10 dilution. If I said, no, I don't want to do 1 to 10 dilution, I want to do 1 to 20 dilution. This is called dilution outside of the usual assay process. I am not following what Stago is saying. Then the result I'm getting is not represented by the analytical measuring range, okay? So the analytical measuring range is the range 3 to 150% without diluting the sample, without concentrating the sample, without doing anything with the sample other than what the manufacturer said. Okay? Now, this is where the confusion is. Linearity and AMR, as you see, they're totally different things. AMR is what the manufacturer claims their methodology can measure accurately. Linearity is how proportional your measured value is to your true value. Okay? So you can be linear, but not accurate, as I told you, okay? Your AMR can be this, for example, but at the end, your machine is saying that things are not linear. So your AMR is all of this, but I cannot use all of this. Okay, so AMR is something and linearity is completely different. Now, AMR verification is, as I told you, because the manufacturer claims that my machine can do this, I have to verify what the manufacturer is saying. I cannot trust what the manufacturer is saying without testing. So I run my test. So I prepare one sample with multiple dilutions. Let's say it's a black line, and I run it on the analyzer. The analyzer measures things correctly. First one, second one, third one, fourth one. Then after the fifth one, the analyzer starts to show a curve. So I say after the fifth sample, my method is non-linear. Non-linear means it's not accurate. I cannot accept it after this point. Okay? So the AMR, according to Stago, is all the 7 points. But after the fifth point, between 5 and 7, measurement is non-linear. So I cannot accept that the whole AMR of Stago is verified. I say Stago's AMR is verified between this point 1 and 0.5 because it was linear. After 0.5, it was non-linear, so I cannot accept it. Okay, so the AMR is not fully verified. Why? Because after 0.5, sorry, it was non-linear. I cannot accept a test that's not non-linear. Okay, so then I can only report results between 1 and 5. Can I report after 5? No, because it's non-linear. Okay, then the range from 1 to 5 is called the reportable range. Okay, RR, reportable range. Did I mention it? Yes, reportable range. Reportable range is the range that I have verified the AMR over. If I could not cover the whole AMR, okay, then that's still the reportable range. So in our example, our reportable range is from 1 to 5. Only why 5 to 7 is nonlinear, I cannot accept it. I cannot report patient results in something nonlinear. If 1 to 7 was all of it linear, I say, okay, my AMR is verified. So my reportable range is 1 to 7. I will ask you, and please, I want one of you to answer. Is the concept of reportable range versus AMR versus linearity clear to you? So AMR is what the manufacturer claims on paper, okay? Reportable range is what the lab has verified to be actually working well on their analyzer. Does anyone have a confusion about this concept? Because this is very important. No questions? Are you sure this is clear? Okay. Now, one small detail. The guidelines available today tell you the following. You can extend your reportable range higher or lower than the analytical measuring range. How? You can dilute the sample more or less than the normal dilution of the method. Okay. And this way extends your reportable range without going into further details. For example, in the case of D-dimer for Stago. Stago analytical measuring range for D-dimer is 0.27 to 4.0 microgram. However, if you run the test actually measures up to 20 microgram. How come? You just said that the AMR is 0.7 to 4.0. Yes, the AMR is the range of measurements where your method is accurate without dilution. Okay, then how come it became a 20? Stago has verified or validated in the R&D that if I dilute the sample further and I measure it, okay, then I can measure up to 20 micrograms. So reportable range can be higher or lower than the AMR, okay, if the manufacturer verified it. But if the manufacturer did not tell you that I have verified this, then you cannot report anything lower than the AMR or higher than the AMR. Why? Because the manufacturer tells you, I don't know if it's accurate. If the manufacturer has verified something higher than that, then you can say, okay, it's accurate, I can report it. Is this clear or not? Should I assume it is? It's confusing. If it's confusing, tell me, because I need to know it's confusing so I can give you guys more details, or I can give you more sources for you to read to understand. Is it confusing for anyone? Please let me know. Well, that's very good then. So this is pretty much what I was explaining to you. So to give you a small example here, visually, the AMR is this, between this point and this point, for example. The reportable range can be something higher as long as it's verified, or it can be something lower as long as it's verified, okay? So reportable range is for range of reportable patient results. Reportable range equals EMR plus extended range if it was verified. Verification is a very important point. If I did not verify that my machine can measure within the AMR plus the extended range, I cannot report results outside the AMR. Okay, even within the AMR, if I did not verify the AMR, then I cannot report the results because the AMR is manufacturer claim. Maybe the manufacturer is lying, I don't know. I have to verify. Okay, this I will skip it, but just for your information, Stago does not offer any linearity materials or AMR verification materials. Some materials you can verify linearity and AMR at the same time. How? For example, CAP materials. CAP will sell you materials different levels with assigned values. Okay, so you can actually, after running these different materials, multiple levels, you can look at the graph that you can draw from these results. Are the results linear? Yes, I say linearity is okay. Are the results accurate? The assigned value matches with the measured value covering the whole AMR? Yes, then I say the AMR is verified. If you are non-linear, say linearity is failed. Okay, and also AMR verification is failed. If you are linear, but the assigned value did not match the measured value, then AMR is not verified, but linearity is verified, for example. So this comes from CAP. Stago does not offer that. Some labs, they do it with their own materials. Maybe they get a sample with a very high fibrinogen and they run it. It's up to them. This is also further information for you, just reading materials. I would not just read over this. This is pretty much what we explained. Now, one small point, linearity acceptable limits. This should be changed to AMR acceptable limits. Okay, but linearity, because a lot of people, as I told you, confuse linearity and AMR, and I fell into this. I just said linearity. It's AMR verification materials. Okay, not linearity. Apologies for that. I'll fix it. This is an example. I'll skip also. Now, one important piece of information. tests reported in second do not have linearity. Okay, why? Because if you have a PT, for example, and a sample that's clotting in 14 seconds, if you do, I want to do dilution, you will not get 7 seconds, obviously. You will get a clotting time that is higher than 14 seconds. So any test that's reported in seconds, you do not have the concept of linearity. Linearity is not applicable to tests reported in seconds. Okay, linearity is only applicable to tests where a concentration is reported. Yes, but fibrinogen is a clotting test. Yes, but you do not report fibrinogen in seconds. You report fibrinogen in a gram per liter in a concentration. Any test with a concentration or activity, you have linearity. Any test that's in seconds, reported in seconds to the patient, you do not have linearity. It's not applicable. It doesn't make sense. Because again, if you dilute a sample and you report in seconds, the clotting time does not correlate with the dilution at all, of course. So this is a bit more details about AMR verification, pretty much what I explained to you. Okay. Now, the range covered in this process becomes the lab reportable range. This means that when you run the AMR verification process in the lab, the range that you cover in your experiment is called reportable range. If the manufacturer have verified reportable range outside of the AMR, then you can use it. If the manufacturer did not verify a reportable range outside of the AMR, you can never report outside of the AMR. Okay? So this is pretty much what this line says. If the reportable range higher than the AMR, okay, less than the AMR, concentration, so on and so forth, that's only if the manufacturer has verified it. Okay? Otherwise, the manufacturer did not clearly tell you that you can report values higher or lower than the AMR, and we have verified it as a manufacturer, you can never report outside of the AMR, which is very important for you to know. Because if you do, for example, if you're a CAP accredited lab, and the lab reported the result higher than the AMR without the manufacturer telling them you can do so, because we verified it as a manufacturer, you will get an unconformity, and the lab will tell you that it was your fault, you told us you can do, Stago verified it. Okay, so you should know this point. This is pretty much further details about the same stuff we explained. This is the example we gave about D-dimer. Now, if my linearity or AMR verification failed, what can I do? If you run this process and you see consistent bias, you can only see bias when you know the assigned value. If you remember, I cannot know bias if there is no assigned value. So if I have consistent bias, you can see bias in AMR verification. So if you see consistent bias in your AMR verification procedure, then probably it's a calibration or reagent issue, as I told you. Okay. If the failure happens at the very high limit or very low limit, like you have seen the black curve, it goes up, then after 0.5 it curves, okay, then likely you have an analyzer issue. In this case, service have to be involved. Okay. How do I know that? You have to look at the linearity curve. If it curves at the end, up or down, doesn't matter the direction, or it curves at the very end, low or down, I don't care. There's a curve. You should involve service because something is not working appropriately. Maybe a needle, maybe a valve, maybe a rinsing well, maybe the reagent is not working well, but something is probably wrong. Any questions about linearity and AMR verification? So should I assume no questions? Things are good? Okay, then I will move on to carry over because it's already an hour and a half. I will give you a 5 minutes break, but please stay around, okay?
Like, can I ask a question? Not in linearity.
Absolutely. Yeah.
Okay, regarding the total allowable error.
Mhm.
Some labs here in Kuwait, they insist on verification. The verification should be done between, for example, Stago and IL. Okay, so the question here is that they keep asking us how to compare, and what I understand, they always rely on the data innovation website.
Yeah.
where you can check the total allowable error, and they compare this, and they can report it in their verification report. Do you recommend this, or
Mhm.
it's a wrong process?
No, and it most probably will not work because
Uh-huh.
see, when you work with total allowable error, there are many things you need to consider. For example, if I want to use total allowable error for APTT, for example, which is the worst example always, APTT. If you compare PTT Automate, for example, to uh, APTTS, I think APTTS or APTTSP from Welfin, the difference will be huge. Plus, their sensitivity is quite different. Plus, plus, plus. So there are many variables that you can have the biggest total allowable error possible. You can have 50% allowable error, and you still fail the comparison. So total allowable error is not really does not really work very well for these things. If, for example, you are using something more standardized, like factor 8, it has an international standard across the board of all the manufacturers. You have, for example, manufacturers who use traceable calibrators for factor 8, so things are more or less standardized. Maybe we can utilize the total allowable error, okay? But there are a lot of equations that come with total allowable error. Using total allowable error blindly without understanding the details can sometimes lead you to accepting things that you should not accept, or rejecting things that you should not reject, okay? The discussion can go into too much detail. I don't want to detail too much, but total allowable error, I would honestly avoid using it to compare between manufacturers. I would generally avoid
Mhm.
comparing between manufacturers, especially in coagulation. Okay.
Okay, thank you.
If you want to discuss this in more details, we can do it case by case because it can get really complicated real fast.
Yeah, sure.
Because
Thank
I
you
know
for
some customers, they go for the data innovation, which by the way takes it from CLIA. Okay.
Yeah,
And
exactly, from Clayan. This is what
yes,
we do actually. Yeah, also for other
yes.
like other manufacturer, but the point is that the QC officers, they insist to use the data innovation. So that's why
Hmm.
I just wanted to clarify this point, because also Julius, my colleague, is here. We need to clarify this point together.
Mhm.
Thank you,
Yeah,
Lab.
yeah, I know it's a bit of a headache, but if you want, we can discuss it more in depth later on,
Okay,
of course.
thank you.
You're welcome. You're welcome, sir. Okay, I think we can, sorry, I think we can continue at this point. So before we start with carryover, anyone has any questions? Okay, I believe then not in this case. So carryover is not a very complex thing, and we have a tool that does the work for you, so things will be straightforward with carryover. Now, carryover is very simply when one sample's contents mix with another sample inadvertently. For example, needle went into sample 1 and run the test. Then, for whatever reason, some of the plasma from sample 1 mixed with sample number 2. This is called carryover. Or for example, sample number 1, when we have done the test, we have finished the test for sample 1, then whatever plasma left from sample 1 was carried over to the next sample, to the reagent, and so on and so forth, okay? So reagent moving into a sample, sample moving into reagent, whatever it is, something that is not supposed to mix with another thing is called carryover. Sample to sample, reagent to reagent, reagent to sample, doesn't matter, okay? So the concept is called carryover. Now, most commonly, this issue is either reagent being carried to a sample, for example, PT reagent being carried to the next sample that should be an APTT test already, only. You should not have a PT reagent in an APTT test, okay? Or sample 1 plasma leftovers mixing with sample 2. These are the two most relevant types of carryover that we have to deal with, okay? So, for example, you run sample and it had a high concentration, then you run a second sample and it has a high concentration, then you run another sample, it has a high concentration, then suddenly the sample after happens to have a low concentration. So the blue is the actual accurate concentration of this sample. However, it reads a little higher, which is not supposed to happen. Why? Because some plasma came from the sample with the high dilution. This is called carryover, okay? So this is not an accurate measurement. See, measured concentration is higher than it should be. Why? Because some of the high plasma came from this sample. This is wrong. It's not supposed to happen, and we call it carryover. So Stagos, normally when you install a machine, okay, they ask you to do a reagent to sample carryover using the biological test sheet, which again is a very strange name for the document, but this is the name. So you would run 10 APTT runs, then the same sample, you would run 10 PT runs, then you would run 10 APTT runs. Okay, why do I do it in this order? Because I want to see the difference between the last 10 APTT runs and the first 10 APTT runs. If there's a difference, then PT reagent probably wasn't washed well off the needle or something happened that's not supposed to happen, where PT reagent affected the APTT measurement, which is again not supposed to happen, and we call it carryover. Okay, so if we detect the difference between the first and the last APTT, we say there's a carryover from the PT reagent. So we call this reagent to sample carryover. There's another type of carryover, as I told you, sample to sample carryover. We have a special procedure for that, but you use two samples. In the reagent to sample carryover, it's one sample, two different reagents. PT reagent, PTT reagent. Sample to sample carryover, it is the same reagent, two samples, okay? One sample, we add heparin to it. The other sample is a normal sample. This is a Stago's protocol, okay? Can I do it in different ways? Up to you. There are guidelines that tell you to do it in different ways. There is no single standard for everyone to follow, okay? And the protocol for Stago to do the sample carryover is in this document. I have given it to you. You should have it there. It's very easy to work with. Now, this is from the biological test sheet. So it's very simple. Number of the test, 1 to 10. So I run APTT on, you can use a normal sample if you want. I run it 10 times. Then I run PT 10 times. Then I run APTT 10 times. Can I do APTT, PT, APTT? No. 10 APTT, then 10 PT, then 10 APTT. Then the average of this APTT minus the average of this APTT divided the percent difference, it should be less than 5%. Where is the 5% here? APTT, mean comparison acceptable value. Okay, and then it will just tell you pass or fail. Simple as that. Okay, this is the protocol or the calculation for the sample to sample carryover from the document I told you about, the 4045. Okay, very easy to do. You can do it even without an Excel sheet. We will not go through that because it's a very simple protocol, doesn't require any experience. Now, this is the point that may be a little confusing for some people. Sample to sample carryover has no exact pass or fail cutoff from Stago because they follow the French guidelines, and the French guidelines say the carryover should be as little as possible. Then what is as little as possible? 1%, 5%, 10%? There are ways to determine the carryover according to CLSI, but things can get complicated if you do that. So some people accept less than 1% of carryover and they say, okay, this is fine for us. Okay. So this has to be decided by the user ultimately, but most users do not do the sample to sample carryover. For them, it's enough to do this and they say, okay, carryover is fine. It's from the manufacturer. We will not do sample to sample. Okay. Now, most often, not most often, really always, carryover failure, if you do the carryover test from Stago, the one in the biological test sheet, and it fails, then that is a hardware failure. Needles not being rinsed properly. Maybe the rinsing well is not okay. Maybe something is blocked. Maybe something is wrong with the needle. Okay, so usually you'd have to involve engineers. Usually application people cannot do much with carryover failures. Okay. Now, this protocol, which comes from AP Evaluator, which a lot of customers, they say, you either do carryover for us this way or you don't do it at all. Now, is this a standardized carryover protocol? No. Does it come from a specific well-renowned guideline? I tried to search as much as possible. I could not find where does this protocol of carryover come from exactly. Okay, AP Evaluator is a type of software that helps you with performance verification or even with validation. And a lot of users know it and use it. Do I have to use this protocol? It's up to the customer, okay? Our protocol, the official one, is from the biological test sheet. Customer wants to use this, feel free. Do I have guidelines for this? No. Okay. So if the customer insists on this, all we can offer is the one from the biological test sheet. If it passes, for us, the machine passed the carryover. Okay. Anything else, we cannot do much for the user because our claim is the one in the biological test sheet. Any questions about carryover? Because we are pretty much done. So I'll stop sharing. I'll take your questions. If you're all done, then we'll stop the recording. Please let me know if you have any questions about carryover. So I'd assume this one also is very clear. Okay, now tomorrow I will show you the documents or all the documents that you will need to use for this kind of work. Okay, so all the documents I mentioned to you today, all the tables I mentioned to you today, I have offered them to you already in the group. I will modify the small mistakes in the presentation, as I told you, and I will send you the verified or the modified version. Yes, Murphy, you raised your hand. Please tell me.
No, by mistake, sorry.
No problem. No problem. Okay, so and then I would assume that you guys have no questions. Radi, I see you are typing. No problem, no problem. Okay, very good. To be honest, yes.
Sorry, are you going
problem.
to explain about the AP Evaluator tomorrow or like
How to use it, you mean?
no, I mean like do you يعني you don't have an official document for this like an Excel sheet, but we can use the AP Evaluator يعني if you have any old documents you can share it with us so that we can see at least.
See, EP Evaluator, yes, you can use it. The problem with EP Evaluator, sometimes the protocols it forces you to use are not compatible with the provided limits from Stago. For example, for carryover, you have to do carryover in Stago's protocol. Otherwise, 5% will be too much for AP Evaluator protocol of carryover. So AP Evaluator sometimes forces you in directions that you don't want to take. So you have to know some things about AP Evaluator before you decide what to do. For comparison, for example, AP Evaluator uses a completely different way to assess bias as compared to what Stago uses. So I just mentioned AP Evaluator here in carryover because this is a common question that comes up. The user wants to use this protocol. Why do you want to use this protocol? Just because it's an AP Evaluator. Yes, but there is no guideline. We are giving you the manufacturer recommendation. So it's something just to clarify that you may have some resistance with carryovers, just for you to know. But
Okay,
I
thank
will not
you.
discuss AP Evaluator more at length. If you have specific things about AP Evaluator, we can discuss them because again, things can get complicated fast with AP Evaluator.
Okay, thank you, Leith.
You're welcome, Sal. So just to wrap up, as I told you, there are a lot of details more that we can discuss about the things we discussed today or that we will discuss tomorrow. But I don't want to cause confusion. I just mean for this to be an introduction. You have some extra details in the slides, but things can get very much more complicated, and this is not the point. I just want you to see that these things can be simple, day-to-day use. They don't have to be complicated. The tools are available. My point is to guide you to what is this thing, you understand it. So if it goes wrong, you can fix it. What are the tools you can use from Stago, so you don't have to search every time, and how to evaluate your performance, pass or fail, because this is pretty much the most important thing. Okay, you know what the procedure is, you understand it, you know how to run it on the analyzers and the customer's analyzer, and you know how to evaluate it, pass or fail. This is what you need in the field. Beyond that, the abstract meaning of this and that, the complexities, the statistics, I don't care. You don't care. You probably will not face it. So if things are more complicated, you need to discuss these things further, you are always welcome to let me know. If I don't know, I will go search for you. So by this, I will wrap it up, and thank you very much for your time, guys. And I will stop the recording now.
Thank you so much, Leith.
You are very much welcome.
Thank you, Lei. Thank you so much.
You are all welcome. I will upload this on the WhatsApp group later on, okay? So you'll have it. All right, then. You all